So, in order to understand the basic science behind the climate crisis, let's start by considering wood. I know, who in the world would begin the discussion of climate science by talking about wood? Perhaps only someone who really loved this particular material, like a furniture maker. So, in case you didn't know, prior to becoming a professor, I spent 2 decades of my life making my living as an artisan, a furniture maker. So, where does wood come from? This might sound like an obvious question, but the answer may surprise you. In other words, if you plant a tiny acorn and wait 100 years or so, it will become an oak tree containing thousands of pounds of wood that can be made into things like furniture. Where did most of that mass come from? Incidentally, I have a UCSB colleague, Lisa Berry, to thank for planting the idea of an acorn in my head in this context. So wood chiefly comes from 4 sources. Interestingly, although somewhat irrelevant to our discussion, these correspond to the 4 classical Greek elements: earth, water, air, and fire. So earth. Without certain elements from the soil, like nitrogen, trees, indeed all plants, cannot thrive or even survive. This is why farmers add nitrogen to the soil, such as through petrochemical fertilizers, and by that I mean fertilizers made from fossil fuels, or organically through plants that add nitrogen to the soil, like legumes. 2. Water. Without water, trees and other plants cannot survive. This is why certain drought-tolerant plants, such as salvia, sages, can survive a drought, while other plants like turf grass cannot. Hence, lawns are a bad idea in dry areas, like here in central coast of California, as their roots only reach a few inches into the ground. In contrast, some sages have roots that go many feet into the ground to access the groundwater down there. 3. Air. As with animals, plants and trees cannot survive without air. Put a plant in a sealed bag and it will promptly die. 4. Fire. Without solar energy, photosynthesis cannot occur. This is why certain growers use opaque plastic for weed control. It's a simple but brilliant idea. If you lay black plastic on the ground and make holes for young plants, for example strawberries, then other competing plants, and by that I mean weeds, cannot grow as they will not have access to light. Weeds may sprout under the plastic, but they will quickly die without the sun's life-giving energy. So, where do you think wood comes from? The wood that makes our furniture and houses. Earth, minerals from the soil, water, wind, air, fire, and by that I mean photosynthesis. The correct answer is, drum roll please, air. Believe it or not, if you're like many people, most of your furniture and a good deal of your house is made of wood. And it all came from air, out of thin air. To understand how this works, we need to consider CO2, carbon dioxide, the principal gas causing the climate crisis. Rising levels of atmospheric CO2 are the primary cause of the climate crisis. Although a range of other gases, principally methane, are also involved, CO2 is the primary greenhouse gas. Although our atmosphere contains relatively small concentrations of CO2, it has a profound impact on plants, animals, and the climate. Since Shakespeare's time, CO2 in the atmosphere has risen from 280 parts per million to a high of 420 parts per million. That's an increase of almost 50%. If 50% sounds like a lot, it should. Indeed, it should be more than a little alarming. So where did all that CO2 come from? In order to tackle this question, we have to consider a little science. Don't worry, I'm a humanities person, not a scientist. I promise it is indeed just a little and not at all tough science. Honestly, it's really pretty fascinating. Plants are capable of doing something altogether extraordinary with atmospheric CO2 when combined with water, H2O, and energized by solar energy. Through the process of photosynthesis, molecules of CO2 and molecules of H2O are synthesized into a range of new molecules. For example, 6 molecules of CO2 plus 6 molecules of H2O become 1 molecule of H12O2, as well as 6 molecules of O2, and that's the atmospheric oxygen that we breathe. As you may recall from high school or college science class, H12O6 is the glucose molecule, a simple sugar. This is a crucial service for all animals, as 6 molecules of CO2 are nicely converted into 6 molecules of O2, which is the oxygen that we breathe. Again, as you will very likely remember from high school, this creates a planetary system wonderfully in balance, as it means that we animals exhale CO2 and take in O2, while plants take in molecules of CO2 and return an equal amount of O2 molecules into the atmosphere. But plants do more, as they also make glucose, as well as a range of similar molecules, such as fructose and galactose. These sugars are essential foods for all animals. You probably are already familiar with them by way of their common name that they all share, carbohydrates, or simply carbs. The carb in the word carbohydrate comes from carbon, as carbohydrates are hydrates of carbon. As a hydrate is simply a substance that contains water, a carbohydrate contains water and carbon and oxygen. Carbon is thus an essential part of the food that we animals eat, whether we get it directly from plants or indirectly from animals that we eat, like cows and chickens that have also eaten plants. In addition to synthesizing sugars like glucose from CO2 and H2O through photosynthesis, plants can create other molecules such as cellulose, which is C6H10O5, hemicellulose, and lignin. Wood is chiefly composed of these three molecules, which, like glucose, are made of carbon, hydrogen, and oxygen. This is also very handy for us. Some plants create edible carbohydrates, which are the basis of everything that we eat, while others create usable material that we can use, like wood. When life on Earth is referred to as carbon-based, as it sometimes is in sci-fi, like the TV series Altered Carbon, it is an acknowledgement that carbon is an essential constituent of all plants and animals on Earth. The human body is 65% oxygen, 18.5% carbon, and 9.5% hydrogen. However, if a human body is dried out, as in the case of a mummy, what is principally left is carbon. Similarly, when we dry a tree's wood to become usable lumber, about half what is left is carbon, as well as nearly as much oxygen. Hence, returning to our original question, all the carbon and oxygen that makes this wood came out of thin air, or more accurately, came out of the CO2 in the air that the tree, because it is a plant, pulled out. Water, of course, also plays a part, but the lion's share of a piece of dried wood's mass comes from CO2. Furniture makers, incidentally, generally like to work with wood that is just 6 to 8% moisture content, and that's water content. Although it sounds a little hard to believe on first hearing, a great deal of our world has been made out of thin air, carbon and oxygen. When we think of natural materials that we human beings use, this is generally the case. Up until recently, when we started synthesizing other materials, which are often made out of fossil fuels, this was almost always the case. For example, all of the following materials are made out of thin air, out of CO2. Clothing made directly out of plant material, like cotton, linen, hemp, and so forth, and indirectly from plants metabolized into animal parts such as leather, wool, silk, etc. Even buttons were made of shells and bone. Clothing were often dyed with that material too, like indigo, which was once used to color blue jeans, though now a synthetic version is generally available. Food, either directly from plants or from animals like cows that turn grass and soybeans into milk and meat. This is worth pausing on, as nearly everything that you have ever eaten, either directly or indirectly, came from CO2, and drank as well, with the notable exception of water, which is just hydrogen and oxygen, as nearly all other drinks we consume are made of plant or animal products. Even alcohol, like whiskey and vodka, is distilled from plant material, such as grains and potatoes. Our homes and their furnishings, as many houses and furniture are principally made of wood, are also made of CO2. Even upholstered furniture was generally made out of animal products such as woolen fabrics stuffed with horsehair for cushioning. A range of supporting materials also comes from CO2. For example, furniture was traditionally finished with things like oil, lacquer, or shellac. We're not talking petroleum oil here, but rather oil derived from plants, like linseed oil. Similarly, traditionally Chinese and Japanese lacquer comes from the sap of a tree, which is collected not unlike maple syrup. And shellac is made of the shells of an insect, the lac bug, dissolved in alcohol distilled from plants. Finally, up until a couple centuries ago, The human world was principally illuminated and powered. We're talking about cooking, heating, manufacturing, etc., by the combination of wood and other plants and animal products, including things like whale oil from lamps. Hence, it is not only that we human beings are made of carbon and oxygen, CO2, our world is powered and filled with things that are made of CO2. Incidentally, all of these things are sustainable insofar as they are all part of the carbon cycle. Not only did these things come from plants, they can return to plants, as everything noted above can be composted. Even cotton jeans dyed with natural indigo can be composted. I mention all this just to get you thinking about it. As we shall see when we move to discuss fossil fuels, a range of products are now created out of petroleum oil rather than plant material. Incidentally, even though they too contain large amounts of carbon, these materials are generally outside of the carbon cycle and hence not sustainable. In any event, when a plant dies and decays, the carbon that it contains, whether in the form of glucose, cellulose, lignin, whatever, generally recombines with oxygen to again become atmospheric CO2. Every spring, plants spring up with new plant growth and CO2 pulled from the atmosphere. Every fall sees the fall of decaying plant material to the ground, where it releases CO2 back into the atmosphere. Hence, global CO2 levels go up slightly during the winter and down in the summer. If you think about it for a moment, everything else being equal, the annual rise in CO2 shouldn't really happen, as it should be offset by the southern hemisphere. In other words, when it is fall and winter in the northern hemisphere, the fallen plant matter, like decaying leaves, should be returning CO2 to the atmosphere. However, as it is simultaneously summer and spring in the southern hemisphere, the CO2 should be reabsorbed by the springing forth of new plants. Hence, the two should cancel each other out. However, because 68% of the Earth's land mass is in the northern hemisphere, CO2 levels go up in the winter in the global north. Follows the north. It's a little more complicated than that, as oceans plants also come into play here, but the northern hemisphere still wins out. Under certain circumstances, plant matter does not decay in the above matter, and this is important, via aerobic decomposition, and that is in the presence of oxygen, which allows the carbon to again form CO2. Although relatively rare today, at least when the whole Earth is taken into account, these conditions were quite common a few 100 million years ago, when the Earth was far more swampy and generally pretty watery. And that's largely because it was warmer, and hence there was little ice on the planet. So, let's take up the question of how plant and animal material, along with the carbon which they contain, can fossilize into fuels that we have. Quite ironically, both made modern life possible and are now threatening it. Incidentally, some climate change deniers, Alec Epstein is an example, like to focus on this point, underscoring that fossil fuels have made the modern world possible. While this is true, it does not mean that we need to continue burning fossil fuels and in the process release vast amounts of CO2 into the atmosphere. There are new alternatives that sidestep combustion altogether, such as renewable sources of energy like wind and solar. In any event, when plant matter falls underwater, aerobic decomposition largely stops, as the decaying process loses access to oxygen and becomes mostly aerobic. Under these circumstances, carbon in the form of CO2 is not released back into the atmosphere, but is instead sequestered underwater and ultimately, under the right conditions, underground. After a few 100 million years of heat and pressure, plant and animal matter is fossilized into what we commonly call fossil fuels. As molecules like glucose, that's C6H12O6, are transformed into entirely new molecules that also contain carbon and hydrogen, as well as sometimes oxygen and certain other atoms. Here are some important examples. CH4, that's methane, which is the natural gas that we cook with. Note that as there are 4 hydrogen atoms, which is the lightest element in the universe, methane is lighter than air and can hence quickly rise into the upper atmosphere. C6H18, which is gasoline, a refined form of petroleum. C240H90O4NS. And that's anthracite, the most energy-rich form of coal. Note also that this fossilized carbon exists in the three regular forms of matter. And by that I mean gas, which is methane, liquid, which is petroleum oil, and solid, which is coal. Note that oil and coal can pick up nitrogen and sulfur during the fossilization process. When combined with oxygen during combustion, these produce oxides of nitrogen and sulfur dioxide, which are worrisome types of point source pollution. Generally speaking, this is what causes smog. Oxides of nitrogen can quickly also act as greenhouse gases indirectly. When methane, petroleum oil, or coal was burned, the carbon that has been buried underground for hundreds of millions of years and hence safely sequestered combines with oxygen to become CO2, the most common greenhouse gas. Methane is a dangerous greenhouse gas even without being burned. Over a 100-year period in the atmosphere, it's up to 30 times more potent as a greenhouse gas than CO2. The chief source of methane released today are hydraulic fracturing for gas and oil, the beef industry, coal mining, and landfills. Methane is responsible for more than 1/6 of global greenhouse gas emissions, perhaps more, again, depending on how you calculate its life in the atmosphere. Roughly a third comes from fracking, a third from the beef industry, and a third from everything else. Returning to CO2, for the past million years, atmospheric CO2 has held pretty steady at 280 parts per million. However, in the past 400 years, it has soared to a high of 420 parts per million. The principal reason is obvious. Human beings have been digging up and burning fossil fuels at an alarming rate and an increasing rate. In 1988, atmospheric CO2 was 350 parts per million. In other words, it took nearly 400 years for CO2 to rise by 70 points in 1988. Since then, in the last 30 years, it has risen by 65 parts per million. This is why some people refer to the period from around 1945 and till today as the Great Acceleration. 85% of the CO2 in the atmosphere has been put there since 1945. Although Americans are only 4% of the global population, 330 million people, 29% of global atmospheric CO2 was put there by us. Conversely, the poorest 3 billion people on the planet have only contributed about 5% of atmospheric CO2. Allow me to repeat that. Although Americans are only 4% of the global population, 330 million people, 29% of global atmospheric CO2 was put there by us. Conversely, the poorest 3 billion people on the planet have only contributed about 5% of atmospheric CO2. Scientists agree that the solution is clear. We need to keep 80% of unextracted fossil fuels in the ground. As 350.org notes, it's not we should do this, or that we be wise to do this. Instead, it's simpler. We have to do this. To understand why, we need to consider the impact that CO2 and other greenhouse gases, like methane, have on our planet and its climate, which will be the subject of the next section in this chapter.